Your database query just scanned 10 million rows to find one record. With the right index, it would check only 23. That's not magic, that's computer science. Today, you'll understand exactly how database indexing works from the ground up. Let's start with the problem. Imagine you have a table with 10 million user records, and you run a query to find a user by email. Without an index, the database has no choice but to read every single row, one by one, checking each email until it finds a match. This is called a full table scan. Its time complexity is O of n, meaning if your table doubles in size, your query takes twice as long. For large datasets, this is unacceptable. So what is an index? Think of it like the index at the back of a textbook. Instead of reading every page to find a topic, you look up the topic in the index, get the page number, and jump directly there. A database index works the same way. It's a separate data structure built from one or more columns that stores values in sorted order along with pointers back to the actual rows in the table. The database can search this sorted structure much faster than scanning the entire table. The most common type of index is the B-tree index. B-tree stands for balanced tree, and it's the workhorse of relational databases like PostgresQL, mysql, and SQL Server. A B-tree is a self-balancing tree structure where every path from the root to a leaf has the same length. Each node can hold multiple keys and has multiple children. The tree stays balanced automatically through split and merge operations as data is inserted or deleted. The lookup time complexity is O of log n. For 10 million rows, that means roughly 23 comparisons instead of 10 million. Let me walk you through how a B-tree lookup works step by step. Say you're searching for the value 42. You start at the root node, which contains a few key values that divide the search space. You compare 42 against these keys and follow the appropriate child pointer down. You arrive at an internal node, repeat the comparison, and descend again. Eventually, you reach a leaf node. The leaf node contains the actual indexed value and a pointer, often called a row ID or tuple ID, that tells the database exactly where to find the full row on disk. The database follows that pointer and retrieves your data. 3 or 4 hops instead of millions of comparisons. Now let's talk about composite indexes, also called multi-column indexes. A composite index is built on 2 or more columns. For example, an index on last name and first name. The data is sorted first by last name, then by first name within each last name group. The critical concept here is the leftmost prefix rule. The database can use this index for queries that filter by last name alone or by last name and first name together. But it cannot efficiently use this index for queries that filter only by first name, because first name is not the leading column. Think of it like a phone book sorted by last name, then first name. You can look up all Smiths or find John Smith, but you can't efficiently find all Johns across all last names. Hash indexes offer a different trade-off. Instead of a tree, a hash index uses a hash function to map each value directly to a bucket location. This gives O of 1 constant time lookups for equality queries. If you need to find the exact value 42, a hash index is theoretically the fastest option. However, hash indexes cannot support range queries. You cannot ask for all values between 30 and 50 because hashing destroys the natural ordering of data. For this reason, most databases default to B-tree indexes, which handle both equality and range queries well. LSM trees, or log-structured merge trees, take a completely different approach optimized for write-heavy workloads. Instead of updating a tree in place, writes go into an in-memory buffer called a memtable. When the memtable fills up, it's flushed to disk as an immutable sorted file called an SSDable. Over time, background compaction merges these SSDables into larger sorted files. Reads may need to check multiple levels, but the write path is extremely fast because it's sequential. LSM trees are used in systems like Apache Cassandra, RocksDB, and LevelDB. They trade some read performance for dramatically better write throughput. A covering index is a powerful optimization. Normally, after finding a match in the index, the database must go back to the main table to fetch the remaining columns. This is called a table lookup or heap fetch. But if the index already contains all the columns your query needs, the database can answer the query entirely from the index without ever touching the table. This is called an index-only scan or covering index. For example, if you have an index on user ID and email, and your query only selects user ID and email, the database never needs to visit the actual table row. Indexes aren't free. There are clear cases when you should not add an index. First, every index adds right overhead. Each insert, update, or delete must also update every relevant index. If your table is write-heavy with few reads, excessive indexes will slow you down. Second, indexing low cardinality columns, like a Boolean or a status field with only 3 possible values, provides little benefit because the index doesn't narrow the search enough. Third, for very small tables, a full scan may actually be faster than an index lookup because the entire table fits in a single disk page. Don't over-index. How do you know if your indexes are actually being used? Use the explain command. In PostgresQL, prefix your query with explain analyze. In MySQL, use explain. The query plan will show you whether the database chose an index scan, a sequential scan, or a bitmap index scan. Look for the type of scan, the estimated rows, and the actual time. If you see a sequential scan on a large table where you expected an index scan, your index might be missing, or the query planner might have decided the index isn't selective enough. Always validate with real query plans. Let's recap. Indexes are sorted data structures that point to table rows, turning O of n scans into O of log n or even O of 1 lookups. B-trees are the default choice, handling equality and range queries with balanced, logarithmic performance. Composite indexes follow the leftmost prefix rule. Hash indexes give constant time equality lookups, but can't do ranges.